morning, everyone. Good afternoon, good evening. Welcome to our Hydrogen 101 Hydrogen and Analytical Tools webinar series. We're just going to let a few more folks trickle in. Really exciting to see all the interest in this webinar series. Great to see you today. We'll just give everyone one more minute and then we'll go ahead and get started. Maybe if we can kick off just to get an idea of where everybody's dialing in from, if you can put the country that you're calling in from in the chat, that'd be kind of an exciting way to introduce people. Great. Got folks from the US, from Asia, South Africa, South America, India. Wonderful. Very exciting. Okay. I think we're going to go ahead and get started. So welcome. Really wonderful to see all the interest in this Hydrogen 101 series, Hydrogen and Analytical Tools webinar series. Really excited to see everybody coming in from around the world. I know it's very early for some, very late for others, but excited to have you here. We're just going to do a quick overview of some housekeeping issues just to kick us off, and then we'll dive into the content of the webinar. So this webinar is being recorded. Just to remind everybody, please let us know if you have any issues with that. That is also so that we can share it with you afterwards. So hopefully this will be a webinar that can benefit you not only now, but in the future as a reference. We are going to automatically mute everyone upon joining. If you do have any comments, then you will have to unmute yourself. But preferably, we ask that you put any of your comments in the chat feature. So you can see this image of the chat button right there if you have any comments or inputs. And then if you have any questions for the discussion, please put those in the Q&A so we can be sure to address those during our question and discussion areas. We are also using auto-generated captioning throughout the webinar, so I just wanted to direct you to where you can set that up. If you go to the bottom of your Zoom screen, you'll see the captions feature. You may see 3 dots for more, and then you can see captions within that. If you select captions, you're going to have to enable it first. So there's a little toggle button. If you can enable captions, then you should have, hopefully, 2 options. One of them is my speaking language, and you can set that to whatever your speaking language is. And then you also have my caption language. If you are dialing in and your settings are in Spanish, then it would be subtítulos. But please select whatever your speaking and, caption language is, and that should enable to have translation, simultaneous caption translation throughout this session in your preferred language. Please let us know if you have any questions. If you have any technical issues whatsoever, you can reach out directly to Isabel McCann, and she will be able to work you through that. You can also adjust your audio settings if you're having any issues to connect or to speak or to hear. You can also dial in. Sometimes that might be clear for folks. So you have your dial-in information, which was sent in the registration email. And just one last thing, at the end of this webinar, we're going to send a survey. It's going to pop up automatically. We would really appreciate if you can fill out the survey. This not only provides us with feedback in terms of the value of the content that was presented today, but also on the future content that we're including in this webinar series, as we would love to hear if you think it's the most relevant content for you, if there's anything you think is missing, and that will really help us to make sure that the remaining webinar series and workshops are as useful and relevant for the audience as possible. So again, for anybody just joining, here are some housekeeping topics. You can just read through them. I won't read through them again, but the most important ones are please set your caption language, speaking language, and preferred translation language so that you can ensure to understand everything that's being presented today. And also, if you are going to be speaking in another language during your questions or discussion, then we can make sure those are translated for our speakers. Thanks very much, and we'll go ahead and kick off this webinar. So again, this is a hydrogen workshop series on analytical tools. We cover a wide range of information. This really has been designed to give you not only a foundation in kind of the basic concepts of clean hydrogen, why it's important, what role it plays in kind of international climate change targets, some technical topics surrounding hydrogen, clean hydrogen, and different types of hydrogen, from production to transport, distribution, storage, delivery of hydrogen. We dive into economic considerations. We dive into market considerations, policy and regulatory enabling conditions. We also look at environmental, social, health, and safety considerations. And then ultimately, we kind of bring all of that together into a synthesis so that we want to make sure that you've really captured all the information that's been presented in this workshop series and can really apply that in a real world context. Throughout the series, we have a format where we have 2 hours per workshop. We have 7 workshops in total. And within each workshop, we hope to present at least one tool, an open source tool that has been developed by the national labs of the Department of Energy of the United States of America. And these tools are really designed to help you understand from a more analytical standpoint all of these different considerations and aspects of clean hydrogen markets. So within the hydrogen to support climate targets, we're going to be presenting the GREET model, which is greenhouse gases regulated emissions and energy use and technologies. This model can be used to calculate life cycle emissions of different types of hydrogen production pathways. But another example of a tool is the H2A tool, which we'll be presenting in workshop 3 on technical considerations, and we'll be looking at using that tool for transparent cost analysis for hydrogen production, either at centralized or distributed facilities. We have a number of other tools as well that are going to be presented within the context of each of the different workshops. And one of our presenters today, Michaud Penev, will be diving a bit into each of those tools, how they're worked, and what are the kind of primary outcomes of each of those tools, how they can be applied within your different hydrogen projects. So again, this is going to be a pretty intensive series of 7 workshops. Today is the first one. We're going to be planning to have these approximately every 2 weeks. So we'll be culminating the last workshop in May. We really hope you can join us through all of these. It's certainly not a requirement. And again, we're looking forward to hearing your feedback on the specific content of this workshop series so that we can also look to improve it for our future workshops. So we'll go ahead and get started with today's workshop, which is focused on Hydrogen 101. We want to make sure we're all starting off on the same foundation, that we have the same basic understanding of why we're talking about hydrogen, why this is important in international dialogue. We'll present a high-level overview of the hydrogen considerations tree, and we'll explain what that is a little bit later. We'll also have a presentation on the U.S. National Hydrogen Strategy and Roadmap, and then we'll dive into some key considerations and tools used for hydrogen market analysis. We have an exciting lineup of speakers today, from Erin Ng, International Relations Specialist of the U.S. Department of Energy. We have Campbell Howe, Senior Strategy Consultant from the U.S. Department of Energy. Myself, International Program Manager at the National Renewable Energy Laboratory. We have Michaud Penev, also from the National Renewable Energy Laboratory, who's a Senior Analyst and Hydrogen Specialist. We have Neha Roustagui, Program Manager of the U.S. Department of Energy and the Office of Fossil Energy and Carbon Management. And then we also have Omar Guerra Fernandez, who's a Research Engineer and Hydrogen Specialist at the National Renewable Energy Laboratory. So really excited to hear from all of these great specialists. And again, just to kind of run through today's agenda. So after this introduction, which we're finishing up now, I'd like to invite Erin Ng, who's going to introduce the Clean Energy Solutions Center, who's funding this workshop series. So very grateful for that. Omar and myself will then present the Hydrogen Considerations Tree, which was developed through the USAID-NREL Partnership, and a really exciting introduction to all of the main considerations that should be taken into account when looking at potential hydrogen markets and projects. We have Neha Roustagui, who will be presenting the U.S. National Hydrogen Strategy and Roadmap. And then we'll have Campbell Howe present takeaways from the pathways to commercial liftoff of clean hydrogen in the United States. And then we'll, last and certainly not least, we'll have a presentation from Misho Penev, who's going to be giving an overview of different Department of Energy laboratory tools for hydrogen supply chain analysis. I just want to mention, we're really hoping that this is going to be a dynamic, interactive discussion and not just us presenting to you guys. So at any point, please put your questions. If it's relevant for the given presentation, we're happy to stop and dive into your question and provide any clarification at that moment. And then we can also address any questions at the end as well. So before we kick off, are there any immediate questions? And if not, we'll go ahead and pass the mic over to Andrew Ng.
Thanks, Daniella. And thank you all for joining today's webinar, Hydrogen 101, part of the Hydrogen and Analytical Tools series. As Daniella said, today's webinar is brought to you by the Clean Energy Solutions Center. The Clean Energy Solutions Center is an initiative of the Clean Energy Ministerial, which is itself a collaboration of 29 countries to rapidly increase the deployment of clean energy technologies globally. The Clean Energy Solutions Center itself is led by the governments of Australia and the United States, and it is operated by the National Renewable Energy Laboratory, which is hosting our webinar today. The whole idea of the Clean Energy Solutions Center is to support developing governments with capacity to design and adopt policies and programs to support the development of clean energy technologies. Next slide. We do that in 3 ways. One is through our Ask an Expert service, and this service is available to any government that needs additional capacity to support a clean energy question or policy issue. And it is available free of charge to developing countries. All you need to do is go to our website and apply to get that question answered. We're very proud of our service, as we've answered over 300 requests in the history of the Clean Energy Solutions Center. We hope to answer many more, including yours. Another way that we support governments is through training and capacity building. We've done over 300 webinars like the one that we're doing today, which are also available on our site as a resource library for clean energy solutions around the world. And finally, our resource library not only includes our past webinars, but it also includes other reports, policy briefs, journal articles, etc., to help support the rapid deployment of clean energy technologies globally. So without further ado, I know we want to get to the meat of the conversation. So I'll hope you all enjoy today's webinar, and I'll turn it back to Daniella. Thank you all.
Thanks very much, Aaron. Okay, so we're going to kick off today's webinar with a dive into the considerations tree, hydrogen considerations tree, which was developed in collaboration with USAID and NREL. This was really designed as a response to all of the requests that we're getting from around the world, and just seeing how many of you and how many countries are represented today, you know, that really reiterates the interest, the international interest in clean hydrogen. In most of the projects that we're working in under the USAID-NREL Partnership, we've been getting requests coming in, you know, how do we approach this hydrogen market? How do we participate in this hydrogen market? What kind of regulatory enabling environment do we need to create to be able to participate in a hydrogen market? What environmental and social considerations do we need to take into account? Do we have the existing infrastructure that we need, or do we need to build new infrastructure? And if so, how much does that cost? What are the health and safety considerations associated with hydrogen? How do we produce it? Should we do it with conventional methodologies, or should we be using only renewable energy? If we do conventional methodologies, such as derived from natural gas or steam methane reformation, how do we do carbon capture, utilization, and storage to ensure that that still complies as clean hydrogen? You know, all of these considerations are really critical, and probably most of all, how is this going to be used? What markets are available? You know, what prices are markets willing to pay for hydrogen, and does that justify the investment costs? Should we even be looking at international markets, or should we be looking at domestic applications? So there's so many questions, and these questions are really critical to be able to make informed decisions, make good decisions for your country, for your project, for your region, that makes sense economically, socially, environmentally. So what we did in response to all of these questions is create this hydrogen considerations tree, which is really kind of an overall training structure to make sure that you're asking all of the right questions, that you make sure you're taking all of the boxes and able to make those informed decisions. So we have a program of 8 modules, kicking off with end use application considerations and then diving into production and energy source considerations. Then we have a 3rd module on infrastructure, a 4th module on cost and economic viability, 5th module on environmental considerations, 6th on social. Then we finally dive into policy and regulatory considerations. And in the 8th module, we synthesize all of that together into a real life or a hypothetical real life case study, which is focused on clean hydrogen and then green ammonia derived from that or synthesized from that. And then certain applications, and all of these considerations really wrapped into that analysis. We use some of the open source tools that are available from the DOE national labs, and then we also run a SWOT analysis. So this considerations tree structure is really designed to make sure that you come out of this with a very solid foundation, you know what questions to ask, and you have the right tools to be able to make informed decisions. So we're not going to be able to dive into this whole considerations tree, but we will share some resources at the end where you can see an executive deck on this considerations tree. We're really going to scratch the surface today, but I think this sets a nice framework for not only the rest of the presentations today, but also the material and content that we're going to be presenting throughout this workshop series. So we'll take a bit of a step back and just ask ourselves, why is everybody so interested in hydrogen? Why is this such an interesting element? Besides being the lightest element, which obviously gives it many physical benefits for energy applications and as an energy carrier, it's also the most abundant element in the universe, which also makes it very interesting. But more importantly, it's just an extremely versatile energy carrier, right? We can produce it from multiple sources. We can produce it from the more conventional approach of steam methane reformation from natural gas. And then when you add carbon capture, utilization, and storage, we start looking at cleaner production pathways from that source. But then we have other really interesting sources from renewable energy, such as gasification of biomass. We even have geological reserves of hydrogen, natural reserves of hydrogen. And then more interestingly, in current day discussions, electrolysis of hydrogen from electricity injected into water to produce oxygen and hydrogen, which is a very clean source of hydrogen, has 0 direct emissions. Obviously, when we look at the life cycle emissions, it wouldn't be 0, but the direct emissions would be. And that's where it starts getting very interesting as an energy carrier to participate in decarbonization strategies. And so, we see so many applications for hydrogen. And this is really where people get excited. You can use it in the transport sector, synthetic fuels. You can use it for fertilizers for agriculture, in metals production for green steel, chemical and industrial processes. We can use it for cement, as well as heat and distributed power. So again, incredibly versatile, so many applications. You can produce it from clean energy sources. And that's really why hydrogen is becoming this ubiquitous discussion in energy sector decarbonization dialogues today. So much to the extent that many kind of refer to hydrogen as climate's Swiss Army knife. It can do everything. It can solve every problem, right? Well, maybe not solve every problem, but it certainly can be considered a Swiss Army knife in the sense that it can be a tool for almost every job. And I think this is a really important analogy because although it can be a tool for almost every job, the question I ask you is, should it be used for every job, right? And this is something that I think we need to think about as we're going forward in evaluating hydrogen for so many different applications is it the best tool for the job? Is it the most efficient tool for the job? If I were to build my house, would I use a Swiss Army knife or would I choose a tool that might be more appropriate for the job? And so I think this is just a really important analogy, as we go forward, looking at when is it the best tool for the job? When is it the most efficient tool for the job or economically competitive tool for the job? And those are really the opportunities that we should be looking at today and as we move forward in our decarbonization pathways. So when we talk about decarbonization pathways, here's an example of a global decarbonization pathway to reach net zero emissions by 2050. And what we see is that hydrogen starts playing a progressively larger role in that decarbonization pathway. So initially by 2030, we're really starting to dive into the development of green hydrogen or clean hydrogen, markets and opportunities. We're really starting to dive into, utilization of hydrogen in green steel, for example, starting to look at e-fuels derived from clean hydrogen, and even other applications, some select applications in the transport sector, for example. Again, very kind of select examples where we see immediate near-term opportunities for clean hydrogen. But as we move forward and as we get closer to that net zero target, that last mile, if you will, it's those hard to abate sectors that really become the most interesting applications for clean hydrogen. And then we're looking at aviation, and e-fuels that can be used as drop-in fuels for aviation, e-kerosene. We can look at utilization of hydrogen for green ammonia, which can be used in the shipping industry and agricultural industry. We look at use of clean hydrogen for cement manufacturing, for heavy transport. And so really, a lot of these very hard to abate sectors become much more important as we get closer to that last mile. And that's why we're seeing much larger contribution within these global targets, 435 million tons of low carbon hydrogen by 2045 as an example. So how do we make these decisions? We've all seen the classic SWOT analysis: strengths, weaknesses, opportunities, and threats. This is one of the great tools that we have to start looking at these hydrogen opportunities. Do we have clean, competitive sources of renewable energy where we're looking to produce clean hydrogen? That's a serious strength and a serious opportunity. Do we have off-takers that are willing to pay a price that makes our project viable? Do we have incentives in our country? Do we have a regulatory framework in place? Do we have a dependable supply chain? All of these are really important questions that we need to be asking when we're looking at these potential projects. But not only the positives, we need to look at the possible threats or weaknesses of those projects. If we don't have a reliable off-taker, is that a risk that we're willing to take? Can we even access finance for this project? And many banks are not too familiar with clean hydrogen projects today because there aren't that many examples. And so, is it difficult to access financing? And in case, is that project not viable? Do we have existing infrastructure that we can take advantage of? And if not, how much is that going to add to the cost of our project? What kind of storage opportunities do we have? Do we have underground salt domes that we can utilize for large-scale storage of hydrogen? Or do we need to build above-ground infrastructure that might add significant cost to our projects? What about transport? Are we transporting 5,000 kilometers, in which case that's obviously going to add a whole nother element to our transport costs? So these are all very important questions. We've included some here in the SWOT analysis just to kind of get you started. And obviously every project is very different, but this is kind of, the types of questions we need to be asking from the beginning to determine if hydrogen projects even make sense to explore further. We can also look at it in terms of a phased approach. So asking kind of key questions from the beginning. Is there a market demand for hydrogen? Or if there's not a market demand, why are we even talking about this? And then are there alternatives available? Is electrification feasible and potentially cheaper than these other hydrogen alternatives? And if so, maybe we want to go in that direction, and kind of going through this sort of flow chart. And the reason we designed this flow chart was in response to, all these questions coming in. Is there kind of an easy way to go through the process of making a decision related to hydrogen? And we thought this flow chart might be a nice way to approach a given project and just make sure that you're asking the right questions and ticking the boxes. I know this flow chart looks a bit daunting and intimidating, so we kind of pulled out a couple pathways just to give as an example. So again, starting off, do we have a market demand? Yes, fantastic. Do we have other alternatives, for example, electrification that might be cheaper, more efficient, more accessible? No. Okay, in that case, let's keep going. Are clean energy sources available? Or if not, do we have carbon capture and storage available to make sure that that qualifies as low carbon or clean hydrogen? If we do, then we keep going. Is the production cost lower than the current market cost or willingness to pay? Yes, very interesting. As we go forward, we start looking at Are there other decarbonization activities that might be cheaper, might be the low-hanging fruit? And if our overall target is just decarbonizing as quickly as possible, maybe we want to choose those instead. If there aren't, then we keep going. Are there any environmental or social barriers that might prevent the project from being developed? No. Fantastic. This is looking great. Is there a local demand for the project? No. Okay, then we start looking at international demand. If there's international demand for low carbon hydrogen, then we start moving forward to the cost, looking at the added costs of storage, transport, delivery, all of those things that are involved with exporting to international markets. Even with all of those added costs, is it still competitive and is it still able to meet the market price? If it is, then we might look at, okay, we're ready to go. Do we have a regulatory framework in place for developing this project? And if no other barriers are identified, we have a promising project. So this is just an example of the kind of flow chart that we can use, or flow process, to make a decision of if this even makes sense to explore further. We might go through that whole process and find that there's a very big social barrier. The community is not supportive of this project. In fact, they're boycotting the project. That could be a red flag, obviously, and that could certainly prevent the project from being developed. And so, at that point, I think we need to start looking back at, what can we do to evaluate alternatives and maybe look for other sites, look for other locations, look for other projects, or can we overcome these barriers? And this is the value of this considerations tree in this flow process, is really making sure that we're addressing all of these potential risks before we get to the point that we've invested a lot of money, a lot of time, a lot of resources in a project that may not be viable. I mentioned the social component because this is extremely important for any project to have community buy-in, right? Not only do you have the policymakers and the regulators that need to be on board, and you need to have the regulatory framework in place, but you also have to make sure you have the buyers and the off-takers that are willing to pay a price that makes your project viable. You want to make sure you have technology providers and that you don't have supply chain issues to ensure that successful delivery of the equipment that you need. You want to make sure that NGOs aren't against the project and, raising environmental or social issues that could ultimately be a red flag for the project. You want to make sure that you're able to purchase your electricity, potentially from the utility company, enough electricity to supply the electrolyzer in the case that you're taking that route. You need to make sure you have access to financing. You need to make sure that you're taking into consideration all of the health and safety issues. And obviously, you need to make sure that the local community is engaged. So, these projects are complex. They involve a lot of people, and really this stakeholder engagement is one of the most important components of developing a successful project. And within that stakeholder engagement, we can look at, land use ownership. So is the community willing to lease the land to us, or do they want to sell it to the developer? If they're not willing to do that, we might have an issue. What is the local perception of the project? Are there workforce opportunities that have been identified and linked to this project? Have we evaluated the value chain and any supply chain risks? We also have to look at water usage. Is there competition for water in the community? In a lot of the communities that we work with in South America, for example, they have water scarcity issues, and obviously hydrogen requires a significant amount of water. So we need to make sure that we're not competing with local water consumption. Or does the project, on a positive side, contribute to freshwater supply if you have a desalination plant, which could then be a positive benefit to the community? Have we considered all human safety risks? We know that ammonia can be corrosive and toxic. We know that hydrogen can be explosive. And so has that properly been taken into consideration? And are there protocols, safety protocols in place? And all of that can be reflected within the regulatory framework. So again, just to reiterate, social is extremely important, and really there's a long list of checklists that we need to go through to ensure that we're complying on the social side for a project. Environmentally speaking as well, we need to make sure that we're considering land availability for infrastructure. If we're looking at, very large projects, we will need land for the wind turbines or for the solar panels, as well as the electrolyzer, as well as all of the storage and transport and distribution infrastructure. So really taking a look at any of those potential land impacts from the beginning is very important. water usage, as we mentioned, waste disposal, how are we discharging brine, sustainability issues, are we using sustainable renewable energy resources where possible? And then obviously going back to, the life cycle emissions, are we considering the life cycle emissions associated with the development of that project? Are we ensuring that this is actually a low carbon or a clean hydrogen project when all of that is considered, for example, carbon capture, utilization, and storage, and upstream emissions? And then we also just want to be sure that we're considering leakage. And so if we have a long distance transport, hydrogen has a global warming potential of almost over 10 times carbon dioxide. We want to make sure that we're considering that and that we don't have leakage. Hydrogen can embrittle pipelines, which can cause leakage. So this is a very important consideration within the infrastructure discussion. And with that, I'm going to leave it and pass it over to Omar, who's going to dive a bit more into the techno and economic considerations of hydrogen that form part of the hydrogen considerations tree. Thanks, Omar.
Thank you very much, Daniela. So, at this point, that social and environmental aspects are very important for hydrogen, but also the end-use applications, right? Like we want to use hydrogen for those applications in which hydrogen is the most cost-effective alternative, right? So we need to make different considerations here. We need to evaluate any other alternative, for example, hydrogen versus e-fuels or versus electrification. For example, if we do have the option to electrify that end use, that may be more cost effective than using hydrogen, biofuels or other alternatives. So this is very important. Hydrogen is very flexible. We could use hydrogen for a variety of applications, but we don't have to do it. We have to do, or to use hydrogen for those applications in which hydrogen is the most cost-effective or the most appropriate alternative. Then we need to evaluate also, different potential end uses, for example, transportation. And here the focus could be on heavy and long distance transportation applications because hydrogen could be cost-effective for those end uses. Then, decarbonization of shipping and aviation. I think those are key important areas for hydrogen because hydrogen could be appropriate for those applications, and we have few options to decarbonize those applications. Also hard to decarbonize sector. This is very key, right? If we want to achieve net zero energy systems by 2050, that means that we need to decarbonize every sector in the economy. So there are sectors that are very hard to decarbonize, and hydrogen could be used for those end uses. Regarding the industrial sector, something that is important here is, do we have industrial clusters? Because this could help us to develop, let's say, hydrogen hubs and reduce the need for storage and transportation infrastructure, because you can, just deliver hydrogen for a cluster of industry using the same storage and transportation infrastructure, for example. Very important, do you have incentive? Which type of incentive do you have? How long are those incentives going to be in place? Because those are going to impact the economics of your hydrogen project. Then we move, let's say, to the chemical industry. Are you closer to a ammonia market or port, for example? For agricultural applications, we need to, ammonia is important for those end users, but we need to evaluate if you are, closer to a agricultural region where you could sell that hydrogen for ammonia production, for example. Also storage. This is very, very important. Storage is, very important not only for renewable energy supply, but also for hydrogen storage in order to meet demand. So we need to take into consideration, let's say, your renewable energy sources. Do you have wind and solar? Do you have hydropower? Do you have any other type of clean energy that could be used to produce hydrogen? Also seasonality. Are those renewable resources subject to seasonal variation that could impact the delivery of that hydrogen? Next, please. So one of the key near-term opportunities is ammonia. Ammonia has a variety of applications. We use ammonia for fertilizers, for energy storage, or for fuel. And today we use ammonia. So this is not a new hydrogen demand. Today we are using hydrogen to produce ammonia. So there is a market already for this chemical where hydrogen could play a role. If we, decarbonize ammonia production, that could help us to deploy hydrogen or clean hydrogen technologies. Key opportunities here, ammonia is cheaper to store and transport than hydrogen. So this could be a carrier that we could use to deliver hydrogen to different end uses, for example. There is a demand for ammonia, so we don't need to create that demand. So there is, less uncertainty around the demand for that hydrogen. Also, we are going to grow as a society. So we're going to need food. That means that we're going to need fertilizer. That means that we're going to need ammonia. So very important end use application. Something that could be important here is, for example, co-location of hydrogen facilities with, let's say, desalination plants in those places where fresh water is not that, or availability of fresh water could be an issue, for example. Renewable energy production, right? Are those ammonia plants near to a good, let's say, solar PV or wind resource locations, for example. And then, we need to think about, just putting together hydrogen and ammonia facilities to reduce the need for hydrogen storage and transportation to ammonia plants, for example. So this is very important, right? Co-location of those systems could reduce the cost in a significant way because hydrogen is, hydrogen storage and transportation is very expensive. Key consideration, we need to evaluate technology readiness level. For example, is this technology that we're going to use to produce hydrogen and ammonia commercially available? Are we competing with any other energy source, for example? Also, ammonia has some safety and health issues that we need to consider as well as hydrogen, right? So those are very important aspects that need to be considered in a more kind of holistic analysis of your business case for ammonia. Next, please. Another, perhaps not important now, but in the future, this could be very relevant for hydrogen, and is the fact that as we move to 100% renewable energy systems or power systems, we're going to need energy storage. And we're going to need energy storage across different time scales. So on the left, you can see a representation of the net load for the power system in California with almost 95% clean energy, including 28% wind plus almost 52% solar PV integration. And on the top, you can see the variation, the hourly variation of the net load. And here, net load is basically the demand minus the availability of wind and solar PV power sources. So if the net load is positive, that means that the demand for electricity is greater than the availability of wind and solar, and then you need, generation from conventional power sources. On the other hand, if the net load is negative, that means that the availability of wind and solar is greater than the demand for electricity, so you have an oversurplus of wind and solar PV power sources. And then when you move to plot B, C, and D, you can see how short duration energy storage, for example, lithium-ion batteries, long duration energy storage, for example, compressed air energy storage or pumped hydro, and seasonal energy storage, for example, hydrogen or fuel-based electricity storage, could be used to do the multi-scale shifting of VRE surplus from intraday to interday to seasonal applications. And for seasonal applications, hydrogen is very cost-effective in comparison with any other storage technology. So I don't see any other technology competing with hydrogen for seasonal storage. So in the future, this could be a very, very important application for hydrogen. Next, please. Now let me talk a little bit about, policy and regulation. We have been talking about social issues, environmental issues, economic issues, and use applications. But policy and regulatory aspects are very, very important. On the right, you can see a summary, or oversimplified summary, I would say, of the hydrogen supply chain. And we need to take into consideration any policy and regulation across this value chain for hydrogen, because those could be really relevant for the deployment of hydrogen. So we need to consider, for example, do we have a regulatory framework for production, storage, and transportation of hydrogen? Do we have any emission reduction targets for a given, end use application or adoption of hydrogen, for example? Do we have incentive, right? Those are very important. Incentives are very critical for those technologies that are at this very early stage of deployment. So we need to evaluate, okay, do we have government incentive for hydrogen? How long are those incentives going to be in place, for example? Do we have a carbon market or pricing mechanism available for low carbon, for example, fuels or energy carriers? Safety standards, very, very important. We don't want to face a catastrophic event with hydrogen, because then we're going to get a pushback from society. So this is very important. Safety and safety standards are very important. Do we have, for example, international certification schemes if we want to deliver hydrogen to a different market in another country? This is very important. I know people have been talking about colors of hydrogen, but we need to move to a more quantitative metric for hydrogen. And if we want to develop a global hydrogen market, we need, a international or global certification scheme for hydrogen. Then, safety protocols and programs for storing and transporting hydrogen, very important again. And finally, international collaboration. This is critical. If we want to establish an international certification scheme, then we need to talk with different countries, with different markets, and make sure that we are speaking the same language. Next, please. Now, of course, the economics are very important, and I am glad that, we first talk about social, environmental, safety issues first, because, as engineers, we always think that, this is about $1 per kilogram or economics, and it is not. Yes, economics is very important, but we need to take into consideration also all of those aspects that we have been mentioning before, including, social, environmental aspects, safety aspects, etc. So regarding the economics, of course, the capital cost is very important. So we need to evaluate what is the cost of our technology, the cost of land for the deployment of hydrogen. What is the interest rate, right? What is the cost of capital? Operating costs, very, very important. In most of the cases, clean hydrogen total cost is driven by the operating cost. So this is very important. You need to pay attention to your operational costs, including clean energy supply. So here we need to evaluate, what is the cost of energy? How will we reduce that cost? Do we have water available? Daniela was mentioning this aspect. This could be really, really critical. For example, in most of the cases, the locations with good solar PV resources don't have, enough supply of fresh water. So this is very important. Economic feasibility, right? Do we have financing options in place that we could use to develop the project? Do we have any investment or tax incentive available? Again, this is very important for the economics of hydrogen production. Market demand, as I mentioned before, for ammonia, you have a market, right? There is a demand. So do we have existing market for that product that we want to produce based on clean hydrogen, for example? Do we have a domestic demand versus international opportunity to export that hydrogen? Market dynamics, right? What are the uncertainties associated with that demand for hydrogen? Do we have a certification requirement that we need to take into consideration? We have a reliable pricing for that product at the end use application, for example. And then any supply chain risk, right? Like, are you going to be available to deliver that power to your hydrogen facility in a 24/7, setting, for example? Or do you have any, infrastructure risk, for example? Next, please. And, Micho is going to be talking more about this tool, but I'm going to present a quick summary here. Hydrogen is a very complex technology, very flexible. So a lot of aspects need to be considered. And yes, we need to make decisions, and we need tools to inform those decisions to make sure that we make the right decision regarding hydrogen projects. So we need to consider different aspects, including, for example, energy sources. What is the availability and variability of those renewable sources? What is the price, dollars per megawatt hour, for example, for that renewable power? Do you have, for example, any climate change risk? in some countries in Asia, for example, or in South America, you have, significant amount of hydropower in the electricity mix. So how is the availability of those resources going to change with climate change, for example? Then, feedstock sustainability and supply chain risks. And here, again, we are talking about water supply, very, very critical. Do we have, for example, if you want to produce e-fuels, do you have a sustainable source of CO2? What is the price of that CO2 that you're going to use for producing e-fuels? Do you have any constraint on critical materials, for example, for the fabrication of electrolyzers? If you want to move from, megawatt scale hydrogen system to gigawatt scale hydrogen systems, for example, do we have any carbon capture and storage potential for blue hydrogen? If you want to produce blue hydrogen, that means that you need to store that CO2, to capture and store that CO2. So do you have options to do that in the place where you want to deploy that hydrogen project? And then, again, technology, technological aspects are very important, right? Do you have, a technology that is commercially available in your country? What about the technology readiness level of that technology? Is something that you can just, buy from the market, or you need to import that technology? And finally, efficiency of those technology. What is going to be the cost for producing hydrogen using X or Y technology? Next, please. Something also very critical here, infrastructure. As I mentioned before, storage and transportation of hydrogen is very, very expensive. So we need to consider this aspect when thinking about hydrogen projects. And here we are talking about, hydrogen and production and delivery. So we need to think about the infrastructure for delivering the electrons, the renewable electrons to the hydrogen facility. Do you have transmission, for example, available to transport those electrons to the hydrogen facility in a different place? Could you just collocate hydrogen production with the existing infrastructure, for example, a desalination plant, for example, a ammonia facility? Do you have storage options? For example, underground storage is very cheap for hydrogen. So if you have this option, this is going to be cheaper than storing hydrogen in any other way. Transportation and distribution. Do you have existing infrastructure that could be used to deliver hydrogen? For example, natural gas networks. Are those materials, appropriate for hydrogen transportation, for example? Then end users consideration. Are you closer to a potential hub for hydrogen? Do you have industrial or chemical sectors around that plant? Do you have, for example, mining around? Because mining could be a key end user of hydrogen or clean hydrogen. And finally, do you have existing production facilities? For example, if you have a ammonia plant that is using hydrogen from estimated reforming, then you could deploy renewable hydrogen technology near this ammonia or steel plant to reduce the carbon footprint of that ammonia. And those opportunities are already in place today. So you don't need to wait for a new demand for hydrogen to be created. Next, please. Then storage. I was mentioning that the storage is very expensive. The good news here is that we have a bunch of options to store hydrogen, including physical-based storage, for example, geological storage. This is very, very cheap. Perhaps but for sure the cheapest way to store hydrogen. So if you have underground facility that could be used to store hydrogen, this is very critical for the deployment of hydrogen technologies. Then you could also store hydrogen as a gas or as a liquid. And then we have also material-based hydrogen storage, including, for example, what is called different liquid or organic molecules that could be used to store hydrogen, or different, materials. This is more kind of storage options that are going to be developed. Some of them are not commercially available now, but hopefully in the near term, those technologies could be available. Something that is very important here is that, the energy density of hydrogen is very low, right? So we need to take into consideration that aspect for storage and transportation. We may want to convert hydrogen into a molecule that has a higher energy density, for example, ammonia, and then store and transport that molecule because it's going to be cheaper. Next, please. And finally, you know, we were mentioning hydrogen or decisions around hydrogen project across different levels. And here you can see a big picture of those decisions across different levels. So we are moving from, you know, plant design and operations, system integration, cross-sectoral applications, infrastructure, storage, transportation, etc. And for each of those decisions, you're going to have a set of tools that could be used to inform decisions that you have to make. And on the right, you can see a summary of different tools that has been developed by the national labs. But something that is very important, and Mish is going to be talking about this, is the financial aspect, because there is a lot of risk associated with those investments. So this tool, H2Fast, in my opinion, is very critical because this tool could provide you with a kind of more financing analysis for a hydrogen project, and then you could understand, okay, what are the implications of different financing options for my hydrogen projects? What is the cost driver of my hydrogen production facility? And then you could focus on reducing those uncertainties around those key cost drivers of your project. Next, please. So this was a quick summary of something that is called the hydrogen consideration tree. So if you want more details, we have, you know, the executive deck, and we also have the fact sheet associated with this material. I don't know, Daniela, you want to say something about this?
No, that's perfect. Thank you so much. And obviously with these QR codes, you can access both of those documents. So hopefully this information will be helpful, and please feel free to reach out to us if you have any specific questions. I also wanted to mention that there are a number of questions in the Q&A. So if our speakers, Omar and also our other speakers, can take a look at those, many of them are kind of more general questions. So we'll try to address those as much as possible directly in the Q&A chat. Thanks so much, Omar.
Thank you.
So we're going to go ahead and pass over to Neha Rustagi from the Hydrogen Fuel Cell Technologies Office of the U.S. Department of Energy, who's going to present on the U.S. National Clean Hydrogen Strategy and Roadmap. Thanks, Neha.
Thank you, Daniella. So in general, the U.S. National Clean Hydrogen Strategy is in alignment with other administration goals, such as enabling a net zero economy by 2050 and enabling 100% clean grid by 2035. So with regard to the first goal, as folks have been saying, we really are targeting the use of hydrogen in sectors that are otherwise difficult to decarbonize through traditional mechanisms like electrification. And with regard to the second goal, that's where hydrogen can play a key role in supporting transformation of the grid by, for example, enabling long-duration energy storage. So if we go to the next slide. So to give a quick lay of the land, today in the US, we produce about 10 million metric tons of hydrogen per year. Most of that is produced from natural gas and is used to supply the petrochemical sector. But something that's changed over the past few years is really an acceleration in the deployment of clean hydrogen production projects. And so that's what you see in the map in the center here, is that deployments of steam methane reforming with CCS or renewable electrolysis have been increasing throughout the country in the beginning due to state incentives, and now also due to all the funding that has come in through the bipartisan infrastructure law and the tax incentives in the Inflation Reduction Act. With regard to end uses, we currently have over 500 megawatts of fuel cell backup power, over 60,000 forklifts that run on hydrogen, multiple gigawatts of electrolyzers that have now been deployed or are past final investment decision. And then in California, also a market for light duty vehicles that's now being expanded nationwide to include heavy duty vehicles. So if we go to the next slide. So the big change that happened a few years ago was the passage of the bipartisan infrastructure law, which included $9.5 billion of funding for clean hydrogen, including $1.5 billion for electrolyzer manufacturing and recycling, through recycling of things like, for example, precious metals, as well as $8 billion for the 4 regional clean hydrogen hubs, which have now been selected and announced. The bill also required that we develop a national clean hydrogen strategy and roadmap, which has since been published and is continually being updated. And then after that, the Inflation Reduction Act passed, which includes a suite of tax credits, including a credit for the production of clean hydrogen. So as a result of these announcements, we've seen an uptick in the deployment of manufacturing facilities for electrolyzers and fuel cells throughout the US. And so very recently, we started plotting announced facilities within the DOE. So for example, over $1.8 billion of private sector announcements in manufacturing of hydrogen fuel cells have been made since the Biden administration began, representing capacity of about 10 gigawatts of electrolyzers per year and about 1 gigawatt of stationary fuel cells per year. And we'd expect that that'll continue to grow as more clarity arises with regard to some of these legislation. So we go to the next slide. So the National Clean Hydrogen Strategy focused on basically 3 tranches. So the first was to target strategic end uses for hydrogen. So this is aligned with what speakers have been saying before, where we want to make sure we deploy hydrogen in places where it's likely to be more competitive than other decarbonization options or likely to have a bigger decarbonization impact. The second is to lower the cost of clean hydrogen. So in support of this, we have targets for both the hydrogen production as well as hydrogen infrastructure. And then the third is to focus initially on regional networks. And the point of this is basically to minimize the cost of capital intensive infrastructure in the early years, and then eventually have networks that can be connected with larger scale infrastructure in the longer term. Across everything we do, we also have funding for jobs and workforce development, which is necessary in any any nascent sector, safety codes and standards, support of policies and incentives, mechanisms to simulate private sector liftoff, which my colleague Campbell will be speaking to later. And then throughout the administration, there's a priority on enabling environmental justice with our funding. So if we go to the next slide. All right, so first I'm going to talk about strategy 1, targeting high impact uses of hydrogen. So some of the sectors we've identified where hydrogen can play a unique role include, for example, chemicals production. So for example, ammonia is a chemical that relies on hydrogen today. So displacing traditional hydrogen from natural gas with clean hydrogen, refining and petrochemicals where hydrogen is also an essential feedstock or an essential part of the process. Long haul heavy duty trucks. So for example, trucks that have to go over 500 miles in one shot, or trucks that operate multi-shift, so have limited downtime for charging or fueling. Those are spaces where it's harder to electrify. Long duration energy storage, so like multi-day energy storage, that's a space where it's harder for technologies like batteries to be competitive. Steel making, so this is a little bit of a niche, but basically virgin steel making that would otherwise rely on coke is a place where you can use hydrogen instead. And then potentially also hydrogen use in generating high temperature heat for industry, or other chemicals like, for example, methanol or synthetic fuels that may be of interest in off-road sectors. And then there's additional demands that could also emerge that we have basically less ability to quantify right now, but things like, for example, export markets or growth of completely new industries. So with all these, within all these sectors, we've identified opportunities for about 10 million metric tons of clean hydrogen demand per year by 2030, 20 by 2040, and 50 by 2050. And that 50 by 2050 represents about a 10% reduction in emissions relative to 2005 levels and approximately 100,000 new jobs by the 2030 timeframe. If we go to the next slide. All right, so next I'm going to talk about the second strategy, which is to lower the cost of clean hydrogen. So next slide, you'll see in all of the stakeholder engagement that we've done, the cost of hydrogen to the end user is seen as the biggest barrier to market adoption. So this includes both the capital cost, which is just a big investment for stakeholders to make, as well as in early years before we get to economies of scale, the levelized cost. So in support of addressing this barrier, if we go to the next slide, the administration launched the hydrogen shot, which is an aggressive goal to enable clean hydrogen production at $1 per 1 kilogram in 1 decade. So that's roughly competitive with the cost of hydrogen from non-clean sources today, and it's about an 80% reduction in the cost of hydrogen relative to electrolysis today. So if we go to the next slide. So within DOE, we have a lot of analysis and then also R&D efforts focused on reducing cost. So there's many different levers we have available. So one of those is R&D to advance basically manufacturing technologies and also to enable large-scale economies of scale. So this can be facilitated by, for example, some of the tax credits, which are accessible for manufacturing technologies, as well as some of the R&D we're funding on manufacturing processes themselves. Other things include R&D to basically reduce the cost of materials or reduce the cost of systems integration within the electrolyzer itself. And that's being addressed largely through our other efforts, like, for example, the H2New consortium that's led by NREL and is specifically focused on reducing the cost of electrolysis. If we go to the next slide. And then the third strategy is focusing on regional networks. So on the next slide, you'll see the biggest thing that we've done in support of this is the launch of the clean hydrogen hubs. So these hubs, within each hub, will have infrastructure that connects production and use. And then the goal is that once these hubs are up and running and deployed, there could be connective tissue that ends up getting deployed longer term and then facilitates basically market liftoff. So if we go to the next slide. So 7 regional clean hydrogen hubs have now been selected. They're located throughout the country, and they'll be advancing over the course of the next several years. So they include hubs that rely on natural gas with carbon management, use renewable and nuclear power coupled with electrolysis, and then also several other resources like, for example, renewable natural gas, biomass, and then a variety of different distribution technologies like pipeline and liquefaction plants. If we go to the next slide. All right, and so across everything we do, as I was mentioning previously, we have these kind of cross-cutting goals, like, for example, energy and environmental justice. And so on the next slide, we'll get into basically that last bullet of environmental justice. And so that's been a big priority of the current administration, and a way that we've been addressing that recently is through funding on how to optimally engage with communities. So if we go to the next slide. So DOE recently released a solicitation that includes funding for permitting best practices to basically address that challenge associated with deployments and to facilitate expedited permitting timeframes. And then also that looks for optimally designed community benefits plans. And so this is basically to help deployments figure out how to work with communities and then also address their concerns. And then in support of that, we also are working on a common concerns document that's in draft form and soon will be finalized, that speaks to basically what some of the frequent questions are that we hear communities bringing up, and then responses that address those concerns. And then if we go to the next slide. So as folks may know, within federal government, one of our requirements is that 40% of certain federal investments go to disadvantaged communities. And so the hydrogen hubs are an example of one of the eligible investments. And so implementation of EJ40 is still ongoing. This is a map that's available online that basically helps folks know which communities are identified as DACs. And then if we go to the next slide. So monthly, the Hydrogen Office has a webinar series where we amplify a lot of new announcements and then just deep dives into particular topics of interest. So I'd highly encourage folks to sign up for our newsletter. If you sign up for that, you'll find out about the webinars. You'll also hear about our solicitations, and then encourage you to check out the H2 Tools portal. That has a lot of kind of just standard information about hydrogen, as well as a database on safety lessons learned. And then lastly, very much encourage folks that are involved in working with hydrogen to explore the Center for Hydrogen Safety. So this is hosted by AICHE, and it's basically a way for stakeholders to, if you join as a member, you get access to DOE's Hydrogen Safety Panel to help with reviews of safety plans for your projects. You also get access to conferences at a reduced registration fee, and then a host of other safety resources. And then please save the date for our annual merit review, which is May 6th through 9th. It's a great way to basically meet folks within the hydrogen space and learn more about what federal government's doing.
Thanks so much, Neha. And just in response to your last slide as well, there was a question in the Q&A on what can companies do that are interested in developing clean hydrogen or clean ammonia projects to access support. So I think you mentioned a number of links there. You obviously have our contact info, but just wanted to mention that if you had any other resources, you could add that in the Q&A. Thank you.
Will do.
All right, now we're going to move on to a presentation from Campbell Howe on a really exciting report that was published very recently, Pathways to Commercial Liftoff for Clean Hydrogen in the US, and she's going to be covering some of the key takeaways from that. Thanks very much, Campbell.
Thank you, Daniella. Hi, everyone, and thanks to the Clean Energy Solutions Center for hosting us today. We can go to the next slide. I really did want to kick off this presentation by providing a quick introduction to the Department of Energy's work on the pathways to commercial liftoff for folks online who might not already be aware of it. But essentially, in order to achieve net zero emissions by 2050, we need to meaningfully scale up our deployment of clean energy technologies here in the US and also globally. And so this will require about $30 trillion of investment capital in the US and $200 trillion globally. The Pathways to Commercial Liftoff is the DOE's effort to help us achieve this goal. First, it fosters a deeper dialogue between the public and private sector. The DOE wants to ensure that our public investments are ultimately catalyzing the private sector capital formation that we need to make these technologies commercially viable. You may have heard this before, but we view our energy transition as private sector led and government enabled. Second, we communicate our learnings through a series of reports. These are living documents that create a common fact base, pulling up-to-date information from best-in-class sources, including market data and industry feedback, research and learnings from DOE's national labs and other teams and agencies, and progress from DOE investments like the clean hydrogen hubs that Neha just referenced. The DOE has published 8 reports to date on a variety of topics, ranging from virtual power plants to carbon management to clean hydrogen, which I'll get into in just a little bit. But before leaving this page, I do really want to call out that the Pathways to Commercial Liftoff is truly a DOE-wide initiative. They're both informed by and help inform other DOE initiatives, and the Clean Hydrogen Report in particular could not have come to fruition without the insights and the collaboration from Neha and from Misha, who are on this call. So we can go to the next slide, please. As Daniella mentioned, we published the Clean Hydrogen Liftoff Report last spring, so March of 2023. In that report, we had concluded that the clean hydrogen has the potential to decarbonize between 10 and 25% of global emissions, especially in hard to decarbonize sectors like heavy duty transport. Last year, we had seen that there were about 12 megatons of announced capacity here in the US, with about 1.5 megatons at the FID or later stages in the project development pipeline. And so if we are to hit the national strategy's target of 10 megatons by 2030, as Neha had pointed out, then the US will require an additional $85 to $250 billion of additional investments. Roughly half of that should go to midstream and end use infrastructure, and the other half to a third in upstream production. However, it's important to call out that a lot has changed even since March of 2023, particularly for a technology that's on the cusp of commercial liftoff like clean hydrogen. So we can go to the next slide, please. I'll touch on this briefly, but we've seen production cost increases over the last year or so due to increases in CapEx costs, financing costs, and other factors. We've also seen the announcement of the DOE hydrogen hubs, which we'll touch on a little bit later, and I know Neha just did, which will represent about 3 megatons of clean hydrogen production in 7 regions. But there's also been an uptick in new project announcements, even outside of the hubs initiative. A third update is that the draft guidance from the Treasury Department has been published on the clean hydrogen production tax credit. This was published in December of 2023. We won't go into detail about the tax credit here, given we're still in the public comment period and guidance has not been finalized, but it's important to call out. And then lastly, the DOE has also announced a launch of a demand side support mechanism with the remaining hubs money to help push forward domestic consumption of clean hydrogen. And so all these factors listed here will influence the commercial outlook of clean hydrogen. And we are currently in the process of updating our liftoff perspective. And we welcome any and all of your thoughts and feedback, which you can email to liftoff@hq.doe.gov. We'll go to the next slide, please. So despite some of those updates that I just listed, I would like to share with you the key messages from our initial report. These largely remain unchanged despite all that's happened over the last few months. So first, we continue to believe that the hydrogen economy is poised for liftoff here in the United States. Given the new pace of project announcements, including the hubs, we are well on our way of hitting that goal of 10 megatons of clean hydrogen production by 2030. The 45V production credit will have a meaningful role to play in liftoff, regardless of how it plays out. It will ultimately reduce production costs and accelerate our transition from high carbon intensity hydrogen, or often called gray hydrogen, to low carbon intensity hydrogen, often a variety of different colors, including blue and green. But even with the PTC, we'll need to drive down production costs so that projects are in the money even once the production tax credit expires. We can achieve these costs down by investing in R&D to bring down the cost of electrolyzers. We can site projects closer to pipelines or to their ultimate point of end-use consumption, and a variety of different levers, which are spelled out in more detail in this report as well. The hubs will also play a core role in de-risking those first-of-a-kind projects and inviting more private sector capital to achieve scale once they're up and running. They'll also be essential to solving midstream infrastructure challenges. And so right now, as I mentioned, hydrogen producers and end users are often co-located or connected through pipelines and trucked very expensively. And so more, and particularly more open access to midstream infrastructure like pipelines will be essential to scaling up this clean hydrogen economy beyond co-located use cases. We're particularly interested in seeing the transportation end uses take off. These present a very large future opportunity for clean hydrogen to capture and to decarbonize everything from heavy duty trucking to bus fleets for maritime and port equipment and aviation fuels. And we believe that that's really the tipping point for a true clean hydrogen economy. One of the challenges right now is that it's hard to get long-term offtake contract for hydrogen, and there are no merchant markets. Producers need that kind of certainty, and that's where the demand side instrument for the DOE is currently coming in. And all of this is really only possible with a strong, skilled, and supported workforce, as well as from support and buy-in of local communities. The hydrogen economy has the potential to create hundreds of thousands of jobs here in the US that will attract and retain workers, so long as that they are high paying and good quality jobs that are supported by strong investments in workforce development and training. And we also believe that the hydrogen development can bring substantial benefits to communities, both here in the US as well as globally, so long as the appropriate stakeholder engagement is conducted. Next slide, please. So this slide is really meant to show just a small, non-exhaustive sample of analyses that we include in our liftoff report that underpin a lot of those key messages that I just walked you through. They range from spelling out the carbon intensities and associated costs of production pathways to analyzing the pipeline of announced projects to comparing production costs with the next best conventional or fossil-based alternative to determine at what point or at what time clean hydrogen might achieve liftoff. Again, I will call out that we are in the process of updating our fact base over the next couple of months with the latest market conditions, so please watch out for updates there. Maybe the next slide, please. So we won't go into detail with too many of those charts that I just listed, but I encourage everyone to take a look at the report to dive into more detail. But I do think we can perhaps use this one chart as an illustration of the kind of analysis that you can expect to see in these reports. I selected this chart largely because it highlights how clean hydrogen is truly multimodal, both across the upstream, midstream, and downstream or end use applications, right? You can ultimately produce clean hydrogen either through reformation or through electrolysis. You can transport it or store it in either liquid or gaseous form, or, and not spelled out here too much, in derivatives. Really what the point of this slide is, or this chart is meant to portray is that 2030 costs across the value chain should advances in distribution and storage technology commercialize over time. And we won't get too deep into these numbers because, again, we are in the process of updating them. For example, the upstream production costs will likely look a little bit higher, and the impacts of the PTC or the production tax credit might look a little bit different. There's also a lot of assumptions that are baked into this figure, and the end use levelized cost is highly dependent on utilization and project siting. The third piece that I'll also mention here is that we haven't called out the whole universe of end use applications. Omar and Neha have shared a bit earlier in this presentation about some of these end use sectors. So I won't spend too much time here other than to say we sort of see a near-term opportunity in the industrial and chemicals use cases, so ammonia and oil refining in particular. But we do believe that transportation, heavy-duty transport in particular, gets very attractive as we look out beyond 2030, which isn't necessarily featured in this chart. This chart and all of the analyses in our liftoff reports are really meant to serve as a shared reference point for public and private sector thinking on this topic and to help align key stakeholders on different strategies to get to that point of commercial liftoff. And if you want to dig in more deeply, again, I encourage you to read the original report or reach out to liftoff@hq.doe.gov if you have comments or questions. So the last slide that I'll call out here is that a big part of how DOE is working towards liftoff is, of course, our hydrogen hubs program, for which we are currently in award negotiations with selected hubs. These hubs stretch across the entire country, as Neha mentioned, and our entire economy. We have large-scale projects in the Gulf Coast and in California. We're making plays in green ammonia in the Midwest, and we're making great uses of some of our legacy infrastructure on the East Coast. Really what's happening is that the DOE is pairing $7 billion of government funding for these hubs with $40 billion of private capital. And so this will truly multiply the capital effect, both in terms of production of both electrolytic and reformation-based pathways. But even more importantly, you know, we're including hundreds of miles of pipelines, including open access pipes, and over 10,000 megatons of storage capacity to really address some of the midstream challenges that we've been highlighting throughout this presentation. And the hubs are also investing tons of billions of dollars for ports and for fueling stations, and for really transportation end uses. They get roughly, you know, 8,000 trucks and buses on the road as well. And all of this is being meaningfully complemented by our demand side support initiative, which will use the remaining money that was allocated towards the hubs program, which was $8 billion in all, to help bridge the gap between some of these delivered costs. So upstream plus midstream towards that end use willingness to pay. So we can now go to that last slide, Daniella, thank you. We continue to be really excited about the prospect of a clean hydrogen economy here in the US. And so with that, I'll close out and turn it over to Misho. Thanks again.
Thanks so much, Campbell. And again, if you could just check the Q&A, if there's anyone who wants to ask a quick question live as well, we have a couple minutes. Otherwise, we'll be sure to address those in the Q&A chat. Okay, thank you so much. And we'd like to welcome Misho Penev, who is now going to be diving into an overview of a lot of the tools, the open source tools that are DOE National Lab tools that can be used for the assessment of different aspects of hydrogen markets and economy, techno-economic analyses, etc. So again, he's going to be giving an overview, and as we move through the workshop series, we'll be deep diving into all of these tools. So thanks very much, Misho. Over to you.
Thank you, Daniella. Next slide, please. So I will be going over some of our technical economics as well as emissions and grid interaction modeling softwares that we use. This is just a snapshot of some of them. A lot of them you can Google on your own, and you can download them for free. But in any case, the first model that I'm going to talk about is the H2A and H2A Lite models. Next slide, please. So the H2A model focuses on everything about production. It does techno-economics from the point at which fuel is delivered to a hydrogen production facility, or electricity is delivered, as well as feedstocks such as biomass, water, be that for process or for cooling of the hydrogen production facility. And it ends the analysis at the point where hydrogen has been produced and pressurized to 20 bar. So architecturally within the DOE, when we model when we model equipment, we model production, which is the H2A model. And then downstream, I'll talk about other models that take that hydrogen, transmit it, or the proverbial midstream, and then downstream applications. So within the H2A model, we have a fairly detailed set of process analyses that cover central production as well as distributed hydrogen production. We have a number of pathways that are available. On conventional side, we have coal gasification. There is a natural gas set of pathways with steam methane reforming with carbon capture and sequestration. Same thing with autothermal reforming, which is a slightly more economic way of doing greenfield hydrogen production from natural gas with sequestration. Electrolysis is one of the major green pathways for hydrogen production, as well as biomass gasification. We also have a few smaller scale distributed production pathways that we keep track of. One of them is electrolysis. Another one is natural gas reforming on site. Those are mostly tailored for smaller applications that are far from delivery routes for centrally produced, cheaper hydrogen molecules. And lastly, this model also has a number of emerging pathways that we're tracking, notably photoelectrochemical pathway, which is essentially, if you can think of a solar type of a panel element that is submerged in water, produces voltage across it and splits water on both sides. So we're exploring some of the more interesting and potentially economic emerging pathways. A couple of things I want to point out is that all of these pathways consider what's called an nth plant production. The costs assume that there is a healthy international production pipeline for these technologies, and it doesn't necessarily reflect today's costs. So, for example, electrolyzers, if they were to be produced in volume, the capex that you will find within the H2A model reflects that high volume of production. If you're interested in modeling today's cost for an electrolyzer, that's going to be a different cost value. Also, the costs are on US-based installation labor basis, so they might be a little bit different for within your country. And of course, some of the feedstock costs, if you just download the model, they're going to be based on US projections on the cost of natural gas, cost of electricity, industrial electricity, et cetera. So those models have the structure, but they're not calibrated for international markets. Next slide, please. Now the H2A models are, it's one model per file. They are rather voluminous. They have many different tabs. There is a steep learning curve for them. In order to make the hydrogen production pathways more accessible for various analysts, including DOE, we have made a more simplified or more user-friendly version of the H2A model. We have replaced the background economics to be handled with a framework called H2Fast, and I'm going to talk about it in a few more slides. This framework is able to do much more rigorous analysis. It is focused on generally accepted accounting principles, GAAP, which is the US framework for financial analysis. Most of international markets do analysis in IFRS, International Financial Reporting Standards. This model is compatible with that if you set the things like depreciation to be in line with how economics are done in your country. So the model itself has a full database of the H2A cases. It has US-based projections for cost of electricity, cost of the various feedstocks. It uses the financial framework I just discussed, and it allows user overrides. So it's heavily leaning on the ability of users just to override things that don't match where the defaults don't match their analysis needs. And then lastly, it provides hydrogen costs and various financial readouts. Next slide, please. This is just a snapshot of what the model looks like. Along the top, you'll see these black buttons. Each one of them, when you click it, it allows you to populate the model with a set of hydrogen production technologies. So if you're not familiar with what an electrolyzer might cost in an end plant type of situation, you can click on the one of the electrolysis pathways or one of the fossil or conventional pathways. You can define your custom pathways as well. On the just as an example, all the yellow cells in here, and as well as if you scroll down this Excel-based model, are opportunities for you to override any of the defaults for the pathway. So for example, if you have a more efficient or less efficient or more capital intensive process than what is portrayed in the defaults, you can override that, as well as you can override cost of electricity assumptions. In a deeper dive, we can discuss some of the other customization options. The model will provide a cost breakdown for hydrogen, and also it will provide a readout of the total cost. Next slide, please. And I'm going to talk about HDSAM next. This is a let's go to the next slide. So the HDSAM model focuses on everything downstream of hydrogen production. So the H2A model goes up to 300 psi or roughly 20 bar hydrogen, and then the HDSAM handles everything that will be considered midstream, so compression of that hydrogen, then consider various modes of transportation, transmission and delivery to end uses. So for example, if we're producing hydrogen in the middle of the country, the HDSAM model is going to consider what kind of compression do you need. If you're transmitting with pipeline, what is the cost diameter of the pipeline, and then at the point of use, if there is a distribution infrastructure, it will paint those out. The model is very focused on transportation as an end market, as that encompasses midstream that could serve industrial uses, but then it also considers what the additional infrastructure would look like for transportation. So if you have to deliver liquefied hydrogen to fueling stations, it will quantify those CapEx, OpEx, as well as levelized cost of hydrogen. There are about 5,000 users at the moment, and analyses have been performed for over 25 countries. So the model is relatively flexible, at the very least, in terms of framework to analyze supply chain distribution. Let's go to the next slide. And by the way, this model is also free to download. If you Google HDSAM, the model is developed by Argonne National Laboratory, so HDSAM ANL. That model is going to populate on your Google search, and you can download the model. Next slide. So the next, we're going to talk about model called H2Fast. Next slide. So the H2Fast model is a corporate finance model, which is very important when you're considering things like incentives, policy tools that might encourage companies to develop certain pathways or projects. The model uses very detailed financial framework. Again, it uses generally accepted accounting principles. It accounts for things like balance sheets, income statements, equity position, statements, balance, income statements, cash flow statements, and balance sheets. Those are the three key reporting standards that are used both by GAAP as well as IFRS. The model uses inputs such as capital, operating expenses, incentives. There are a number of different ways to provide incentives, such as upfront capital incentives that, for example, we were looking at for the hydrogen hub financing. If you're looking at tax credits or income-based incentives, those can easily be modeled. So in the US, though, that would be things like operating incentives in California that are being used in California, or the Inflation Reduction Act. There are a number of different incentives that are based on tax credit, operating tax credit. The model allows the users to provide different scenarios. So if you want to look at side-by-side analysis of should you do something with sequestration or not sequestration, or if you should do different mode of production or distribution of hydrogen, if you want to model, the incremental cost of a pipeline or a compressor, the model is set up in a way that you can model different alternatives for supply chain elements, as well as put them side back to back to see what the total cost of delivered hydrogen is. There is a bit of art to that. The model has, it's free to download, and also it has about 2 or 3 hours worth of video recorded instruction on how to use it. So people that want to have more nuanced analysis, they can do that. It provides additionally some risk analysis. Some of the inputs for techno-economics have uncertainty associated with them. For example, if you don't have a good handle on what the interest rates might do, you can tell the model, I think the interest rates are most likely to be X, and it might range from this and this level. Then the model will provide you a readout of what the impacts of that risk look like. Next slide, please. The next model is the SARA model. This is one of the models that is actually not available for free downloads, just because it's very computationally intensive. There is a steep learning curve to it. We run it on our in-house supercomputer, just because there are a lot of moving pieces to it. The model is geographically distributed, and it optimizes delivery and production infrastructure so that you can achieve certain rollout targets. It considers energy resources, it considers existing production pathways, and then connects supply and demand, also builds out any additional production facilities over time in order to achieve the demand growth for hydrogen in various locations throughout the United States. The model also has, it goes into a little bit more detail on the transportation side. So if you're looking, where to site hydrogen fueling infrastructure, it will do that for you. Or if you're just interested in industrial scale hydrogen, which is not as finely distributed within urban areas, the model is flexible to set up those types of scenarios as well. At the bottom, there is a link that provides some reading material about the model. But again, Unfortunately, the model is not available for downloads. It's more of a something that we run for DOE and other folks. Next slide, please. So I'm going to brush into the GREET model. Next slide. This is a life cycle analysis model. So basically having to do with emissions from hydrogen production. It's actually, the model is keeps track of not just hydrogen production, it keeps track of a lot of other pathways. The model has been around since 1995. It keeps track of other things like steel production, if you want to see what is the default energy intensity and emissions intensity for steel production or for cement. It has a lot of different pathways, but the one we're going to talk about is hydrogen. The model is free to download. It has about 50,000 registered users globally. Along the bottom, you'll see that the model keeps track of upstream, so well to pump emissions. It considers everything from the extraction point of conventional fuels or generation of electricity. It looks at all the emissions. It has US-based coefficients for what percentage of the natural gas, for example, may be leaking, or if you're having coal supply, what emissions are associated with upstream activities, such as the extraction and delivery of that coal for a coal gasification, let's say, or if you're generating electricity and you have emissions associated with combustion or construction of solar panels, etc. It would account for all that upstream emissions. It would also account for hydrogen facility emissions. So if you're electrolyzing the hydrogen, obviously you would not have any criteria pollution or carbon emissions at the site of production. But if you had a facility that is sequestering or emitting CO2 into the air, it would account for that. So that is the what's called the GREET-1 model. Everything upstream up to the dispensing of a fuel or consumption of the fuel. There is also an additional GREET-2 model, which focuses on the vehicle side or the point of use side. So if you have a vehicle that is consuming a certain flavor of fuel with certain emissions profile, it will tell you what are the on-roads or what are the emissions associated with the operation of that vehicle per mile driven. Next slide. This is a little bit more detail about what pathways are specific to hydrogen are available within the model. We have conventional pathways, such as the use of conventionally extracted either shale or other type of natural gas. It looks at the distribution as well as the conventional steam methane reforming, where CO2 is vented to the atmosphere. To the right, upper right figure, you can see some of the cleaner pathways where you might have conventional pathways coupled with carbon sequestration, or you might have biomass gasification technology or electrolysis that converts electricity to hydrogen in order to produce hydrogen and also byproduct oxygen. Some other pathways recently were added is autothermal reforming. This is a more efficient way of doing natural gas with carbon sequestration. It basically uses air separation unit to provide oxygen for the reforming process, which results in a concentrated hydrogen stream and a concentrated carbon dioxide stream, making it a little bit easier to concentrate and provide that carbon dioxide for sequestration. There are emerging pathways such as methane pyrolysis. This pathway uses natural gas and electricity to produce hydrogen and solid carbon in various forms, be that carbon black, all the way to nanotubes, which may be structurally interesting products. And also there are co-product pathways such as hydrogen that is co-produced with chlor-alkali. Next slide, please. So this, I'm just going to highlight that there is the Greek model itself has a very steep learning curve. And we're using the model for qualifying certain facilities, what their carbon emissions are and how much tax credit they're going to have from our Inflation Reduction Act incentives, in order to make the model more accessible to US producers, as well as I would assume for international purposes. There is a new interface that is available for hydrogen production, where you can select your analysis year, production pathway. You can customize how much electricity or what the conversion rate is for that hydrogen. You click a calculate button and you get your emissions profile. So again, these models are free to download. These are links to the models. Next slide, please. And one more. One of the models that is available, again, for free is the StoreFast model. Omar mentioned that hydrogen is envisioned to take to serve as a long duration, either seasonal or monthly storage for electricity to allow decarbonization of the peaking capacity for the US grid. I would imagine that a lot of the countries that are on the call have a lot of seasonality as well, either from the point of renewables availability or from the point of demand for electricity and how cyclic it is. When we look at seasonal shifts of energy, it is very important to have a very cheap way of transporting that hydrogen, that energy from one season to another season, without having to have substantial overbuilds of renewables, or without having to use more expensive and more efficient pathways, such as, for example, lithium batteries tend to serve more of the up to 10, 12 hours worth of duration. But if you need something that's on the order of 120 hours or 5 days of storage, or if you need something that is meant for perhaps a month's worth of storage of electrons, then we get into hydrogen technologies where the storage of an additional kilowatt hours is relatively cheap, especially if you have formations such as salt domes, or bedded salt formations, or hard rock outcrops that can be converted for hydrogen storage. So this tool provides a benchmark for different technology options for this very extremely long duration of storage. One thing I want to point out is, as one of the previous speakers mentioned, hydrogen is a Swiss Army knife of technologies. If you were to build a long duration energy storage system, the physics of it works out in a way that you end up having the opportunity to overproduce hydrogen, which can then improve the economics for operating that facility. So in here you can find examples of if you produce hydrogen, store a lot of it. Maybe sometimes you use it for peak power generation. Some other times you use it for just supplying other markets. This model would be able to quantify that for you. Next slide, please. So lastly, I'll speak to, I'll go over briefly over the rodeo model. This is a, and by the way, Omar can speak, is an expert in this model and could speak a lot more intelligently about it. But basically, it is a price taker model. You put a hydrogen production facility in the environment of different utility connection schemes. Either you connect with renewables directly, or you connect with your local utility, and you look at the retail schedule of, what does it cost to purchase during the middle of the electricity, middle of the day, or end of the day, if there is a time of day type of differentiation in prices. It gives you a way to minimize the cost of hydrogen and figuring out how do you dispatch the electrolyzer so that you get the lowest costs, you minimize the amount of storage that you need for hydrogen, and at the end of the day, provide a smooth offtake of hydrogen for various uses. In the next slide, I have a brief example of what this looks like. So in the bottom left, you can see different scenarios that were modeled. I'm not going to go over all of them, but for example, one of the scenario is to connect hydrogen directly with a set of resources, be that solar and wind. That would be called an islanded scenario, where the resources are not able to provide excess electrons to the grids, and the grid is not able to provide electrons to the electrolyzer when the wind and the solar are not available. So that's one scenario. Another scenario might be that you produce electrons and you sell them to the grids, and then separately you pay distribution expenses and you download those electrons from the grid. So this would be a separated scenario. There is a retail scenario where you purchase electrons under different rate structures that are available from the utility grid, and so on and so forth. And what the model does is it figures out what is the best dispatch, temporal dispatch of the electrolyzer in order to achieve lowest costs of hydrogen. To the right, lower right, you can see a time-based series of how the electrolyzer is dispatched to give best cost. And then on top, you're going to see the techno-economic results for the specific set of scenarios that was run. Now, the model itself is open source, however, and you can download it. However, it relies as a mixed integer linear programming model. It relies on relatively complex solvers. So typically you would need to have you need to purchase one of these solvers to integrate it with the model. There is quite a bit of a learning curve to using the model, but we have expertise at NREL and documentation that one can tap into. And that's my last slide. I think the next thing on the agenda is Q&A.
Thank you so much, Misho. Really exciting to have this overview of all the tools, and hopefully everybody that's listening in, all the participants, are also equally excited to start deep diving into these tools as we progress through this workshop series. So we wanted to open it up for any live questions or comments from the participants. Could be questions or comments specifically to Misho's presentation or any of the prior presentations as well. I think we've been doing a pretty good job of addressing all of your questions in the Q&A in written format as well. But if any of the responses, if you'd like further clarification on any of them, please let us know as well, and we'd be happy to elaborate. Looking for any hands. Anything in particular that you guys found more interesting or relevant for your particular countries, regions, projects?
Danielle, it looks like there's a question in the chat.
Okay, let's see. Is there any specific occupational health and safety program for hydrogen technology? Okay. Misho, do you have a response on that one?
So in Neha's presentation, she had on the last slide of her presentation, she had a number of resources for that. There is an international resource, as well as there are, yeah, that's scrolling all the way to almost, yeah, keep going.
That one. Oh,
no,
nope,
yeah,
nope, the other one. I
keep
got you.
going. That's the,
There we go.
there we go. So the bottom two resources there, those have to deal with hydrogen safety. Actually, both of them. One of them is a free resource. The other one, I believe, is a paid resource to participate in, various codes and standards activities.
Great, thank you. So we have another question. Can you please share the presentation on the software? We're going to be sharing the entire presentation from this webinar, as well as the recording, so you'll have access to that. And then also on the software, we'll be deep diving into those in subsequent webinars. We have a question. Where does the US government draw the line for clean hydrogen? Is there any document or link where we can learn the definition?
So there are a couple of documents on this. Again, on this slide right here, upper left, you can see the US National Clean Hydrogen Strategy and Roadmap. It has definitions for what clean hydrogen is, as well as it has elaboration on what the plans are for the United States. And obviously there is the liftoff report that, that we had a presentation on. And those, yeah, both of those documents are available free to download.
Great, thank you. So someone is asking, how can we make a comprehensive framework using the software that you presented? And where can we find help?
Yeah, I think that will be a case-by-case basis, but yeah, within the tools that the DOE has been developing over the last couple of decades are mostly available for folks to use. We have at NREL specifically, we have worked with, for example, different regional hubs in order to quantify what hydrogen would look like in the context of regional resources, prices, hydrogen demands. So, we've seen people do their own roadmaps or work with, third party or maybe perhaps even NREL to develop those types of roadmaps. Typically, we will do analysis with the SARA model, which kind of pulls together the different models to arrive at a stepwise progression of what do you build first, what do you build second, where do you put a pipeline, and kind of gives you a time series of where and when and how much investment, et cetera.
Great. I think we had a live question from Janelle, but I don't see your hand up anymore. Janelle, did you want to ask your question?
Janelle, I just gave you the ability to.
Can you hear me?
Yes.
Okay, I have a question. So can a hydrogen project used in a waste to energy project?
Yeah, so there are a number of different flavors there. There is a solid biomass, depending on what the water content of the biomass might be. That biomass might be best handled with what's called an anaerobic digester if it's really wet. There is if the biomass is dry, such as forest residue or municipal solid waste, construction residue, there are pathways for gasification. So it depends. If there is anaerobic digester, you can use the biomass for basically reforming, doing steam methane reforming for and converting it to hydrogen. But yeah, we definitely have been looking at things like landfill gas, dairy manure, and then solid feedstocks. There is also interesting opportunities for converting plastics and gasifying. So if you have plastics that are not recyclable and their fate is either to go into a landfill or to be incinerated, there is also another option which is to gasify and produce hydrogen through that route.
Great, thank you. We have another live question from Rojosoa. Can we unmute Rojosoa?
Yep, Rosa, you should be unmuted and can speak now.
Okay, thank you so much. Someone can hear you well?
Yes.
Okay, thank you so much to give me a floor. Thank you for the best presentation for today. I think that I got a lot of knowledge concerning the model, especially for me, because I'm working on that. So for me, I have one question concerning the model. The great model, I think this model it is just for this this topic, like a system vehicle, or we can use it with another topic, for example, a waste treatment or a waste to energy. So so is there by the several models that you presented for us for today, any suggestion for me by the several models that you presented for, because I'm working on the waste treatment or waste to energy. Thank you so much.
Yeah. So yeah, with most of what we presented today was to produce completely go to clean hydrogen so that you can use it in various applications as a standard fuel, be that in vehicles or perhaps electricity generation or things like that. If you're only interested in producing electricity, some of the waste pathways are probably more economic to convert to what's called either a syngas, where you gasify and you get a mixture of carbon dioxide, methane, hydrogen, and then you can run that through a combustion process to produce electricity. Or you can look at gasification pathways again. Anaerobic digestion pathways, depending on what your feedstock looks like. If you're just looking to incinerate a product gas that is result of a waste stream, you don't necessarily need to go all the way to clean hydrogen. Clean hydrogen might have a higher retail value than that electricity for various reasons. But again, some of the upfront conversion processes would be equivalent, whether you're going all the way to clean hydrogen or if you're stopping somewhere in between where you get a combustible gas that can be used in power generation.
Okay, thank you so much for the clarification.
We have a question here from Misha as well. I'm working on a techno-economic analysis with policy framework, including infrastructure from scratch. Which of the softwares that you presented might be the most suitable for that application?
So I've seen this effort on a few different times, and typically people look at the H2A models for hydrogen production to look at what the production looks like, and then they typically would go to models such as HDSAM to quantify midstream, how do you get that hydrogen to your various end markets. One thing to note about HDSAM is that it's a true Swiss knife of a model. It is designed to take demands into transportation markets, but if you open it up, it has a lot of great details, such as cost of pipelines or compressors. So if you want to use those moving pieces to design your own supply chain, that's a great resource to data mine for different supply chain elements, techno-economic performance. So typically, when we're talking about individual projects, you would typically use the hydrogen production model and HDSAM, and you can frame out individual projects. If you're looking at a much bigger picture, such as a national roadmap, you might want to consider things like the SARE model, where you can have multitude of projects, perhaps from different companies, and you can see how those individual projects add up to a national objective for decarbonization or hydrogen, supply.
Great. And I think we have one last live question from Barbara O'Neill. And with that, we're going to wrap up the Q&A. Apologies to anyone we weren't able to get to. I know we're at time. Please make sure if we didn't get to your question, put it in the specific Q&A, and we'll be sure to respond to those. And you can also feel free to reach out to us as well. Can we unmute Barbara for one last question?
Barbara, I gave you permission to speak. You might have to unmute yourself.
Hi there, can you hear me?
Mm-hmm.
Yes, Barb, I can hear you.
Hey, Misho. So I'm just wondering, if we should place more emphasis on that transport infrastructure, and this is for really all the presenters, and get really clear about what needs to be built from scratch versus what can be modified from natural gas pipeline infrastructure networks.
Yeah, no, that's a very good question, and that there is a lot of research happening in the United States on how much hydrogen can we blend into existing infrastructure, how much of the infrastructure can be converted to 100% hydrogen. So there is definitely a lot of ongoing research and analysis in that area. One of the cheapest ways to transport hydrogen would be via pipelines. Ultimately, that's where things need to go for it to be economic at significant scale. That's probably deserving of its own 2 or 3 webinars.
Okay. Thank you so much, Misho. Thank you to all of our presenters. Really exciting, great kickoff to our webinar series. We really hope you'll continue to join us for our upcoming series. You can see the next one here. You can register for already, February 21st, and we'll be sending out more info based on your surveys as well. Your survey is going to pop up as soon as you log off of this meeting. Based on the info from the surveys, we'll modify and adjust the upcoming webinars to make sure that it suits the greatest interest of the audience and participants. So really look forward to receiving your feedback. Thanks so much for joining us, and we look forward to seeing you in the next one. Bye, everyone. Have a great day.
Thank you all.
Thank you.
Thank you.